Today we are dealing with the orthogonal projection. In the last class, I think you have seen just a brief, was given a brief on the orthogonal projection and perspective projection. So this is nothing but under a projection transformation. So projection transformation has two projection kinds, orthogonal projection and perspective projection, which is very, very important with respect to the exam point of view, very frequently asked. So that means projection transformation is how the object is projected onto the screen. In what way the object is projected? There are two ways, that is orthogonal projection and that is perspective projection. So what happens with respect to the orthogonal projection is the two ways. So that we will see. Ma'am has already told you what is orthogonal projection. Orthogonal projection is nothing but you have 2 points P1 and P2. The same object should be projected onto the view plane. Fine. Onto the view plane is nothing but, the view plane is nothing but which we actually see the object. How do we see the object is actually first projected onto the view plane before projecting onto the device screens. Okay, so it is nothing but P1 and P2 I have the same point is projected. So let us go in deep how the orthogonal projection actually is dealt and perspective projection. So first orthogonal projection, a transformation of object description to a view plane along the, so transformation of the object description. For me, the object is actually a line, P1 and P2. There's a line. This object description to a view plane, I have a P1 dash and P2 dash onto the view plane. Along the parallel lines. So with the help of these parallel lines, I am able to project onto the view plane, that is P1 dash and P2 dash. Okay, and this parallel lines is actually a parallel to the normal vector, which in the last class it has been discussed. Normal vector is this to the view plane. So always a parallel lines is parallel to the view planes, normal vector n. So these are the lines. These lines, dotted lines, what we are seeing here is called an orthogonal projection or an orthographic projection. Okay, is an orthogonal projection or an orthographic projection. We call it as orthogonal or orthographic projection. This produces a parallel projection transformation in which the projection lines are perpendicular to the view plane. So there is another way of explaining your parallel projection transformation. That's nothing but these dotted lines is actually perpendicular to your view plane. You agree? This is perpendicular to your view plane, but see, it is perpendicular. It's perpendicular to view plane, but it is parallel to the normal vector. It is parallel. Check here. This is a normal vector, but that is perpendicular to your view plane. Fine. This is nothing but an explanation of your orthograph projection that I call this. This is called as a orthographic projection. Okay. Okay. So next slide. Usually orthographic projection is most of the time used to see the front view, side view, rear view, top view. Okay. So for that we have a name called elevations. The front view, we call it as a front elevation. Side view, we call it as a side elevation. Back view, you call it as a rear elevations, and top view we call it as a plane view. Okay, so front, side, rear is we call it as a elevations. Top view we call it as a plane view. Okay, so this is most of the time these projections, it is defined, which you can apply just to see the front, because when you go and see your CAD labs and all, that is nothing but it is a model understanding. You just have to see the model. Okay, you pull it front, pull it back, however you pull it, move around across your XYZ direction, the size of the object remains same, or size of the object actually remains same. There in a CAD, my main intention is to see the object's angles or object's parts very clearly. Okay, so orthogonal is only meant for that, to check the any kind of a model designing, right, where the size of the model will never change even though you move across. So you can see here in the front elevation, you will get these, whatever you can able to visualize, this complete you're getting as one part, and this. So the size of the object what is drawn here, in the same size, the front view is actually shown here, right? So that's an orthogonal projections. Projection is, see, you have done lot many projections here. Lot many projections here. Okay, this is a front projection. In the same way, for every point, with respect to every point, the projection line is actually drawn. Fine. In an orthogonal projection, we have a concept called axonometric and isometric orthogonal projection. Let us see what is axonometric. Axonometric is nothing but orthogonal projections which show more than one face of an object. So most of the time you will see only front view, only you will see most of the time only one face. Side face, back face you will not see. But axonometric is where you can see more than one face. So this blue color line, whatever you have seen here, this will be your view plane. Okay, so this will be your object. So now the object is projected onto the view plane. When it is projected, how many faces you can see? I can see 3 faces here. 1, 2, and 3. Okay, so that's why one object where it is in such a way it is projected onto the view plane where we can able to see more than one face. The definition we call it as axonometric orthogonal projection. Such kind of projection we call it as an axonometric orthogonal projection. In axonometric orthogonal projection, we have one more concept called isometric. Fine. What do you mean by isometric? The way you project your object. Okay. All isometric is actually axonometric itself, projection. In isometric, you can see the, if I say this is your origin, the distance from the origin to the plane, projection plane. My projection plane is exactly on this. From the distance from this, how many faces I'm able to see? 3 faces. And on the projection plane, this distance, and from this distance to the projection, that we call it as a principal axis onto the projection planes. Every distance is same. Okay, so that means we call it as an isometric projection, orthogonal projection under axonometric. Even though I could see more than one faces, the distance between, in the center origin, from the origin, the distance to the view plane is same in all the object. Fine. Or these planes. This is one plane. This is the second plane. This is a third plane. To those plane, the distance is same. The distance is same. So that we call it as a isometric projection. Orthogonal projection coordinates. So that means, how do we deal with the coordinates here? So you can check here with the projection direction parallel to the, usually projection direction, how it will be there? Always projection direction will be parallel to your Z view axis. Yes or no? You agree? So yeah, when you see here, these are all the projection direction. If this is your view plane, if this is your view plane currently, the Z axis will be always here like this, which is parallel to the normal vector n, which is actually parallel to all of your projection lines. With the projection direction parallel to Z view axis, and for any position XYZ in viewing coordinates, now they're saying you have an XYZ, it's in a world coordinate system. Say that's an object, it's a point, considering as an object currently. The projection coordinate, what will be my points on the view plane? So it's nothing but X and Y. Always when you project onto the view plane or your screen coordinate, it will be in a 2-dimension only. Fine. So let us not worry about this Z currently. I'll tell you why. So only two. One is X direction and one is Y direction. Only two position, two coordinates. So then if the point, the object which is in the world coordinate, if it wants to project onto the view plane, what should be the points of in the view plane? So the point is nothing but the projection point xp yp will be equal to x, yp will be equal to y. So this will be nothing but our xp comma yp, which is actually equal to x comma y, because it is parallel. My points will never change. The angle of the line will never change. So it is exactly the same pixel, whatever I have in the world coordinate can be projected onto the view plane. So it is very easy in my orthogonal projection that if x and y, if I have xp, the projection, x projection on view plane and y projection on view plane will be same as your world coordinate. Then what happens with respect to the z coordinate? The z coordinate value for any projection transformation is preserved for use in the visibility determination procedure. You will learn after these topics. You will learn visibility determination procedure. What is this visibility determination? You will learn very clearly. I'll just brief you. When you have two objects, so now if you see, this is, I have one object here, and I have behind this, I have another object projected here. So then based on your camera, you have to say that which is visible and which is not visible. Who has to decide? I have to do an algorithm to decide whether this object should be first or this object should be first, front. So based on what I will decide that? Based on the Z value, I will define that. Fine. That will be a visibility determination procedure. Visibility determination procedure. So to Z is actually mainly used in these algorithms. Fine. Next. Now, very important is we have got to know, we have learned about the projection lines. We have understood the simple logic is nothing but the coordinates. If any object, if I want to project onto the view plane, the coordinate values, what is in my previous coordinate system, maybe a world, maybe a we have a center coordinate is a viewing coordinate system. So any coordinate system, maybe a normalized coordinate system, there are many coordinate systems. Before going to the viewport, wherever, in whichever the position the x and y of my object is there, in the same position, it is parallel, it is positioned onto the viewport. That we have understood. Now, very important is what all I have to project onto the view plane. What all I have to project onto the view plane. When it comes in this picture, for example, if I take a camera, the camera lens takes a major role, right? How much ever the lens angle we have, only that much portion of a object is actually defined. How much I need to see in computer graphics, we use the rectangular clipping window. So we use a rectangular clipping window. So rectangular clipping window gives me the how much, what all I should see, right? So that means most of the time, the rectangular clipping window, based on the OpenGL package, some of the package will ask us as a parameter, how much your limits, your clipping limits you want. That's nothing but your lower left and upper right corners, threshold. If I give the threshold based on my ortho or whatever it is, my clipping window, I can give it, define it. But the many open packages, especially I think OpenGL packages, will not give such options for the user. It is fixed. Right? The positions are, the position of the clipping window is fixed. The clipping window, what I can say, values is based on the user. That's how you will give your ortho values. Okay. Now, the position is fixed. Where actually I have to place a clipping window? The clipping window lower left gives me the XW min and YW min. Upper right gives me the XW max and YW max. Okay, this is my clipping window values. If these two values, if I give, the clipping window is actually defined. For three-dimensional viewing, the clipping window is positioned. Yes, the position is fixed. Okay, the values is based on the user inputs. The three-dimensional viewing, the clipping window is positioned on the view plane in three-dimensional, because the view plane concept we don't have in two-dimensional. However you rotate, whatever you do, I have already drawn only with respect to two dimension, I will get only two dimension. There is no much complexity in the two dimensions. Okay, so the clipping actually I do in a very early stage, and the same thing I project. But here in three dimension, we prefer the clipping should be done in the later stages. You have seen our viewing pipelines. You would have seen model coordinates, world coordinates, viewing coordinates, normalized coordinates, and the viewport coordinates, and then comes to the screen coordinates. So clipping will be done, preferred to be done at the last stage. So always the clipping is placed on the view plane, the position on the view plane with its edges parallel to the X view and Y view, which is a view. It is nothing but your view plane. So this is parallel to the X view. The Y axis of the clipping window is parallel to the Y view. Okay, in such a way it is placed on the view plane. So now what all we will do with respect to the clipping window? Once clipping window is defined, I will take the X and Y limits of the clipping window for the part of the scene that we want to display. Obviously, we know that clipping window is the limits I will give, X limits I will give, and Y limits I will give, so that my object, what I need to be drawn is a part is seen, a display is displayed onto the clipping window. Which part of my object should be seen is actually displayed on the clipping window. So I have an X limits and Y limits. So now what they're saying is, these limits are used to form the top, bottom, and two sides. Top, bottom, and two sides of clipping region called the orthogonal projection view plane. So see here, you can see in a top view, in a figure, top view B, the figure B, I am projecting throughout the edges of the clipping window, and then I am trying to get the orthogonal projection view volume. You will understand what it is. Because projection lines are perpendicular to the view plane, these four boundaries are planes that are also perpendicular to the view plane and that pass through the edges of the clipping window to form infinite clipping range. So I am giving this as a range. Whatever I do pass, that is passed to the onto the view plane also, right? That is perpendicular to the view plane also, because in my previous video I have already told clipping window is positioned onto the view plane. So wherever the view plane is there our clipping window is there. If I see all this line is passing through these edges, then obviously it is perpendicular. If these lines are perpendicular to the view plane, the clipping window, then it is perpendicular to the view plane also. Fine. Then what I can do, I can generate infinite clipping range. I am defining the range here. I am projecting it front and back, both I'm projecting. I am setting what? The range I'm setting. What is that range? We will see here. See, this is the range. What did I do? From the previous picture, I have drawn the lines which is perpendicular, projecting lines perpendicular to the clipping window. So with this, what I did, I made the range, defined the range. Now it was in my previous slide, it was an infinite clipping region. I have defined the infinite clipping region. Okay, now I should make it as a finite clipping region. The finite clipping region is nothing but gives me based on the two planes. That is based on the Z view direction, based on the Z view. Which is your Z view? You can see here. This will be your X, this will be your Y. The Z is like this. Fine. Z is like this is your right hand system. Correct? This is your right hand system. My positive Z is towards you. My negative Z is away from you. Is that clear? So that means check with the Z. The Z goes on like this. Correct? So that means I have extended my boundary of my clipping window based on the Z view direction. Okay? Whether it is a minus Z view direction or plus Z view direction, it's up to us. How do we want to extend? So when we extend our view volume, I call it as a view volume. When I extend our orthogonal view volume, what I will do, before I had an infinite region, I will make it as a finite region. What is a finite region? I pull up with the two boundary planes, which is parallel to the view plane. So this is what the two boundary planes. One is this plane, one is this plane, two boundary planes. The other one is this plane, right? The other one is this plane. I have pulled these planes. I have defined these two planes. I have positioned these two planes based on the ZY axis, considering the Z view direction or Z view value. And I have taken two planes. One plane is actually a near plane, I call it as. One plane, I call it as a far plane. So the two planes are called as near far clipping plane, or also called as front back clipping plane. Now I have got the finite range of orthogonal projection view volume. Is that clear? Why do I need view volume? It is 3D. I am drawing a 3D here. Whatever the object, okay, we can see here, whatever the object is outside of these volume. So if I have drawn, it's like this, okay. It's 3D. So that means because in 3D, I have z-axis also. So if I would have added only 2D, I would have retained only clipping window, which is there in 2-dimensional. But as in 3D, 3D objects have a z value, then I have to keep the z kind details in my view volume, because I need to keep clipping or clipping my objects with respect to x direction, with respect to y direction, as well as with respect to the z direction. Now, this complete portion is clipped off. This complete portion is clipped off. This complete portion is clipped off. Only this is projected onto the clipping window. So this is my volume because I have z-axis also. Fine. With the view direction along the negative z view axis, we usually have z far less than z near. So that means what they say, usually in viewing direction, what happens, here in this, you can see here, our z far will be this, z near, because I've already told you z near is this and z far is this. So they say z far is less than z near. So that means z near will be your positive, z far will be your negative values, because it is a right-handed system. If you keep it, you can see your z-axis is towards you. So towards you is a positive, away from you will be your negative. From the origin, here it will be 0. From here to here it is negative. From here to here it is positive. Okay. So that's why they say in this viewing direction, z far is less than z near. So that the far plane is farther out along the negative z view axis. It is in the negative direction. When the near or far planes are specified, we obtain a finite orthogonal view volume that is rectangular parallelepiped. So that is nothing but the finite orthogonal view volume. Hope you have understood this. Why view volume is required. Now we actually here in the last class, now we have understood that we need a view volume. So now once a view volume is done here, I told you projecting every point onto the clipping window is very easy because it is direct, it is parallel. Whatever the x value I have here, it's the same value x value it will be onto my clipping window or onto my view plane also, view plane. Now, so we don't have to worry how I need to project it. What will be my coordinate? My coordinate will be same. Fine. Whatever the coordinate value I will have in this object, the same coordinate value I will have on the view plane or a clipping window. Now, object projection, I don't have a problem in orthogonal projection. Then what I have, the next one, now we have to consider what is that we need to do now. We need to normalize this. Do you remember we have a view planes, too many, what I can say, stages of a view planes, where we have seen, as I've already told you now, currently I just told you that model coordinate I have, I'll just write here, I have a model coordinate, I have a view coordinate, I have a normalized coordinate, and I have a viewport coordinate, then it will become a device coordinate. Fine. So these two usually we have not worried converting from these to this. Do you remember model to world coordinate? Sorry. Okay, this will be a world coordinate. So we have a model to world coordinate. So this also we didn't worry much. But you have seen our previous section. Do you remember? We have converted window to viewport. Please, if you have that, see to that you open that. Window to viewport. We converted window to viewport, right? While converting to window to viewport, what did we do? There was two steps. First, directly we converted window to viewport. Our viewing was not there before. So then, next what did we do? We converted window to normalized and normalized to the viewport. There was a two stages we did. Hope you remember that. But now in this viewing, as we have defined orthogonal and perspective, from window we have to go to the viewing. Now from viewing, what I should do? I need to, in many cases or OpenGL cases, normalized and viewport will be together, right? That's what we dealt at. If it is together, what will be my matrix? If it is not together, then this viewing should be converted to normalized. From the normalized, it has to be converted to the viewport, right? Hope you remember that. Please open that matrix. So now, that is what they're telling here. Using an orthogonal transfer of coordinate position onto the view plane, we obtain the projected position of any spatial point. If spatial point only, it is in the world coordinate. As I've told you, we will project as it is. My x and y will not change in orthogonal projection. Now, once we have established the limits of the view volume coordinate descriptions inside this rectangular parallelepiped are the projection coordinates. Correct. Now we have to map this to the normalized view volume without any further projection processing. I am not doing any projection, that is point projection processing here, because we have already defined whatever is there in the world coordinate as xy will simply be the same in the viewport also, view coordinate. So projection processing is not there. Then what we need to take care? I need to see to that my rectangular parallelepiped should be mapped to the normalized view plane. So that means here the rectangular, here what I had, here a rectangular parallelepiped need to be converted to a normalized coordinate, because before I put it onto the viewport, fine, which is similar to the device coordinate, before I put it in the device coordinate, it has to be in the normalized form because it is easy for me to convert. We have already discussed this, right? So now, before doing that conversion, we have a slight problem. What is that problem? The problem is our viewport, this, okay, here. Let me erase. Okay, so here we need to convert, right? This viewport, what we had a rectangular parallelepiped in this region, okay? Rectangular parallelepiped. This is an right-handed coordinate system. That means your Z is towards you. Z near is positive. But the device or screen coordinate system, can you see your screen here? What coordinate system you will expect for your screen? I just wait for your answer. What kind of a coordinate system you expect here for the screen? Right-handed coordinate system or left-handed coordinate system? So when you see your screen coordinate will be in left-handed coordinate system. So, but basically all your world coordinate and viewing coordinate system, everything till normalized, whatever additional they can have coordinate system, everything will be in RHS. So now from RHS, it has to get converted to the left-handed coordinate system. So this is a position when you have to convert from RH. So this is my main thing here. So what, because screen coordinates are often specified in the left-handed reference frame, normalized coordinate also are often specified in the left-handed coordinate, because in normalized, what is normalized? I am bringing normalized coordinate system here as one extra only because at the last, I should not, while converting into the screen coordinate, I should not have any time consuming. It should be easy for me to convert. As we have already discussed, multiple screens, what we have is in a different size. So my complexity is actually in the screen coordinate system where I have too many options here, When I have too many options of size of the screens, I will see to that my previous object from where I'm getting my coordinate system, the object is defined. That should be a simpler way for me to get multiplied. So I keep it as only a zeros and ones here, 0 to 1, which should be easy to convert to any size of the screen. Fine. So I will keep this normalized, whatever the screen coordinate is there. I will not take, otherwise it takes for me an extra time to rotate and all those, change the direction, translate, all this composite matrix, again it takes time. So I will not keep any kind of a complexity here. So whatever the screen coordinate I have, left-handed coordinate system, I'll keep the normalized coordinate system as it is. See, this is my screen. They're giving the screen X and Y. So obviously towards this you don't have any position. So you expect this will be a positive Z view axis. Positive Z view. So that means near you what happens? It will be a minus Z view axis. Okay. Thus, what is our main goal? Thus, we have to convert projection coordinates into positions within the left-handed. So now where are we? We are in a viewing coordinate system, which is in the right-handed. That is our rectangular parallelepiped is in the right hand. Now that I have to convert into the left hand now. So let us see what will be our viewport transformation. So this is my viewport. While transforming to the viewport, what will be the new viewport transformation or in the normalized coordinate system? To illustrate the normalization transformation, we assume that the orthogonal projection view volume is to be mapped into the symmetric normalization cube. So now this is my normalized. What do you think? Normalized. So this will be a parallelepiped. Okay. Most of the case, it will be a parallelepiped because my ortho I will define. However, I define the parallelepiped is volume, orthogonal view volume is set up. Now, however, it can be with X min, Y min, X max, Y max, Z near, Z far values. I will convert this to the normalized view volume. So you can see the normalized view volume is a cube. It's a cube, which is a left-handed. Now you can see both. One is left-handed. This is right-handed, and this is left-handed. Is it clear? Okay. So last class, I think, ma'am, in the last class you have seen when the coordinate systems are different, it was like this. This was a Z view. This was X, Y. So this is X, Y, and Z. If this is the case, in the last class we have discussed, how do we actually project this left-handed to the, sorry, right-handed to the left-handed or left-handed to the right-handed? I need to translate this origin first to this, right? I need to translate. Then what I should do, once I translate this, if I want this Z to come on this plane, then I have to do what? Rotate, or vice versa. If you want this to be kept here, translate, and this Z to be rotated to this direction, then you have to do what? Rotate. So this was your matrix, was discussed in the last class. Hope you remember that. So that we have to take care. Apart from that, now I have to take care with respect to coordinate axis. I have done it. Coordinate axis done. But with respect to the points, because the size of this orthogonal parallelepiped is different from the normalized. My XW mean, YW mean, Z near value is different. But here normalized, it is -1, -1, -1 in the place of XW. Now, this we will keep it aside. This rotation and translation, we will keep it aside for now. Now, how do I convert my each and every point, X, Y, Z point, to the normalized view volume? Hope do you have that matrix Sx and Tx we have converted and we've seen? Now, you please open that and check. This will be your window. This will be your viewport. Because it was a window to viewport conversion, my window will be there, my viewport will be a normalized viewport. So this is nothing but a normalized viewport. So what was the definition of that? Please open that matrix. So now my positions will be X min, Y min. All X min, yes. X min, Y min, Z near will be equal to -1, -1, -1. X max, Z max, Z far will become to 1, 1, 1. Transforming the rectangular parallelepiped view volume to a normalized cube is similar to the methods for converting the clipping window into the normalized symmetric square. Please open that and keep. The normalization transformation for the orthogonal view volume is this. I think you have got, we have done this much. This is not there, and this part, right? And this part. Now we have to check this part. Correct? Now, for this was your, what is this? This was our Sx, right? Sy, this is Sz. This is Tx, Ty, and this will be a Tz, right? All Sx, we had a formula. So open that Sx formula. By seeing Sx formula, I will start writing Sz. Fine. So what will be the Sz now? Hope you have that Sx now. Keep your Sx. Sx was okay. Sx was xv max minus xv min. Please open that. Xw max minus xw min. You don't have to write all these derivations. Directly you can write the matrix if you remember. So now, this now I'm converting into Sz. So what will be Sz now? Sz will be Zv max minus Zv min divided by Zw max minus Zw min. So this will be my Sz, which is that disposition, which I've written this part. So now, how I've got -2, let me erase it a little bit. Okay. So I need to check this and this. So this is your Sz and this is your Tz. Okay. Now I have to get Sz. So what will be your Sz? Please go back. Check here. This will be window. That is nothing but ZW. All ZW value will be this. All Z view, that is a viewport, normalized viewport value will be this. That is a normalized value. So what will be your Z? This is your X, I don't want. This is your Y, I don't want. This is your Z. What is this Z? This is your Z near. Check it here. ZW. This is your Z near. So your Z near, that is nothing but ZV min. Z near is equal to ZV min, which is equals to -1. In the same way, Z far is equals to ZV max, which is equals to 1. That is this part, which is equals to 1. Okay, so let me take those values. So here they have given. So that is ZV min. ZV min is equals to -1. ZV max is equal to +1. Right? ZW min is equals to ZW min is equals to ZW min is equals to Z near. ZW max is equals to Z far. Correct? From the previous figure I have taken. So now I will replace this. XZ is equals to ZV max is how much? +1 minus of ZV min is how much? -1 divided by what is ZW max? It is nothing but Z far minus ZW min is Z near. So they've just worked on with the minus value. Fine. So they've taken common 2 divided by same thing Z near minus Z far. That is with respect to SZ. Okay. Now will you work out with respect to TZ in the same way? And please try to get this one, TZ. So the TZ value also you have. Whatever the TX value you have, convert that into a Z. As I've done from SX to SZ. And you will get this value. So this matrix is nothing but the point by point conversion from ortho to normal. What ortho view volume, orthogonal view volume to the normal view volume. Okay. Now what is left? R and T, which I've actually decided, we just checked here. Yeah, R and T. R and T for what? Converting a right-handed coordinate system to the left-handed coordinate system. I need to rotate what my axis. That is R and T. So this will be multiplied. This complete matrix will be multiplied with the rotation and transformation. Now the whole object will come and sit into the normalized view volume. Thank you.